Hello, students. This tutorial will summarize what we really need to understand about the pressure that gas particles exert. So on the very front of your student note packet, these are the things that we've addressed over numerous days and with numerous demonstrations and so on. And so you know you can always see me, send me an email if you have any questions regarding any of these. Also, in the student note packet, beginning on page 8, I actually have pages from the section in your textbook regarding gas pressure, just because it is such an important concept for us to be able to deeply understand, and that you know that you have the support of other literature here as well. All right, so where do we begin? Well, what is pressure? Pressure is defined as force per unit area. Well, how do gases do this? So if we think of a balloon, we know filled with gas particles with very, very high kinetic energy. And we can imagine that these particles are moving in a straight line until they encounter another particle or the walls of the container. And so they're moving back and forth and back and forth. And we talked about how fast and so on. But invariably, they are going to collide with each other and the walls of the container. Forces are any pushes or pulls. So gas particles push in that they hit into each other, exert forces per a certain amount of area. Now, of course, pressure can be changed by increasing or decreasing force, but also by changing the area over which the force is exerted. All right, so we understand these forces are because of the collisions of gas particles with themselves and the walls of the container. And so this is what we really want to be able to imagine. And it's this that leads to gas pressure. Okay, well, what can we do to increase or decrease the frequency or forcefulness of collisions? So the variables that impact pressure are the number of particles. The greater the number of particles, the greater the frequency of collisions. The less particles, the less frequent, therefore the lower the pressure. You can also change the volume. The greater the volume, keeping this constant, the less they're going to collide. The smaller the volume, the more they're going to collide. And then temperature. Temperature is directly related to kinetic energy. If we increase temperature, we're increasing kinetic energy. So the particles will collide with more frequency, but also more forcefully. And if we decrease temperature, the opposite. So these are the variables that we can change to then change pressure. All right. Well, ever since you were born, you have experienced atmospheric pressure. We're surrounded by nitrogen and oxygen and other gases, and they are behaving like this on us. If you were at the surface of the earth on a fair weather day, and you could extend a column around you up to the outermost reaches of the atmosphere, where space begins, and add up all those collisions, that weight or forcefulness on you, excuse my use of imperial units for a moment, is 15 pounds per square inch. So this part of your arm is feeling the weight of 15 pounds, and this part of your head, and this part of your leg. But we've always experienced it. We are going to know that this relative value in chemistry, we assign to be 1 atmosphere. So at sea level, on a fair weather day, that is what you experience. Well, How do we measure atmospheric pressure? A gentleman by the name of Evangelista Torricelli invented the barometer. And in essence, a barometer is a long test tube that is filled with mercury. So imagine taking a test tube, filling it entirely with mercury, covering it, then overturning it into a bin of mercury. So if we could imagine, and it's usually about 1 meter high. And what happens, this initially is filled, but then when the lid is taken away, the mercury falls. There's nothing above it. This is a vacuum. And we put graduations. And from one day to another, we measure the height of the mercury. And the mercury level rises and it falls. Well, what is in control of that mercury height in the tube? Well, the atmosphere is on the outside, but it's also exerting pressure on the liquid that can be pushed in or be allowed to flow out, depending upon the forcefulness of atmospheric pressure. We directly measure the height of the barometer, which the height of the mercury is controlled by the strength of the atmosphere. So again, at sea level on a fair weather day, the height of this can be found to be approximately 760 millimeters of mercury. That is equivalent to what we call 1 atmosphere. Well, eventually, we thought we need to honor the guy who invented the barometer. Remember, his last name was Torricelli. And so we said, well, yeah, it's 1 millimeter of mercury, but what if we just rename 1 millimeter of mercury from the reading of a barometer a torr, after Torricelli? So we could say 760 millimeters of mercury, or 760 torr is equivalent to 1 atmosphere. So if perchance you read the barometer and it reads 745 millimeters of mercury, well, we could find what it is in atmospheres by simply using this relationship of 760 millimeters of mercury in every 1 atmosphere. These will not limit our sig figs. The given measurement would. And so we could find what the reading in atmospheres would be. But we have another pressure unit, and that is a Pascal. Very frustrating that we have torr, millimeter mercury, and atmosphere. Here we come along with a Pascal. Well, there are 101,325 pascals that are equal to 1 atmosphere. Quite honestly, we usually reference a kilopascal. So there'd be a 101.325 kilopascals in 1 atmosphere. I will provide these. We don't have to memorize these relationships. Millimeters of mercury come directly from reading a barometer. So we're going to be working with eudiometers and some other things in lab. And so we're going to see these show up lab-wise. And a lot of chemists prefer atmospheres. And we're going to see next chapter, there's a constant that we can rely on that needs our pressure to be in atmospheres. So we're going to have to rely on converting between millimeters of mercury and atmospheres and vice versa the most. But sometimes we'll also be converting into and out of pascals and kilopascals and atmospheres. So those are the relationships. All right. So if we go back, so we've talked about common units for gas pressure, what is atmospheric pressure, what causes gas pressure, how can we change gas pressure, how do we measure it, meaning how does the barometer work? And then we did the demos. So we want to be able to explain why, remember, we had the pop can on the hot plate that was filled with just a couple of milliliters of boiling water, and we could see the water escaping out the lid. And a student overturned this into, probably 1 degree Celsius liquid water, and the can got crushed. Well, what caused that? Remember, we had an Erlenmeyer flask, and we put a burning cotton ball inside and put a hard-boiled egg without its shell, and it ended up inside the Erlenmeyer. So what would explain that? Remember, we did things with a vacuum, we talked about suction cups, and then be able to, and we talked about this in class, explain how you use a straw step by step to get the liquid into your mouth to enjoy. All right, that is gas pressure. You know, as always, you can send questions, concerns my way.